In this lesson, we'll be analyzing the structure. Before we go on to analyze, we have to check if the model is okay. I'll start by editing the wall loads and removing the wall loads I don't need. Don't select and hit delete on your keyboard. It will delete the beam also. So what you have to do is to pick on the wall loads you want to remove. Right click, then delete beam wall load. Yes. Edit this wall load. Right click, edit beam wall load. Reduce the height of the wall to 0.9 because it's a parapet wall. I'll copy this wall load and paste it along the edges of the 6th floor along these beams. If I get here, it's going to override the existing wall load. To do this easily, I have to come to the 6th floor, go to my plan view, take it to the 6th floor. Then the view tab, active windows, settings and interrogation, visual interrogation, beam wall loads. Right click, copy beam wall load, and now select these beams at the edges. Okay, let's deselect and take it back to our 3D view. This is okay. Let me move to the 5th floor, take it to plan view, the 5th floor, do the same thing here. I'll hold down Ctrl on my keyboard to select multiple beams. You can make more modifications to your model, but I will skip that step and move to editing my stories. So I'll come to stories, right click, edit story, and this is the story number, the story height, the story level from the reference. I can give a description for each story. Let me call this Eaton office, market and office. And you can fill the rest if you want to, but I'm just going to leave CEO at the end. And this is the length of the building along the direction 1 axis and the length of the building along the direction 2 axis. Okay, and let me show you this. So this is the floor 1 to 4, floor 5, 6, 7, and this is D2, D1, D1, D2 for the other floors. Why the red dimension, I use it to signify the center of gravity for the building. Minimize this. If I want to apply impose load reduction, I'll come here, impose load reduction, and I'll apply. And if I want to consider the roof adequate for life load reduction, I will come here, apply, and this is okay. Give my first story bottom level 450, and you know the first story bottom level is the distance from the natural ground level to the top of the ground floor. I'm using 450. I can give my footing a label of F, and I can call the footing, let's say, pad foundation. When I'm done, I'll click OK. Yes. Okay. There's a faster way for me to modify multiple elements at the same time. I'll come to Members tab, the Members table. If I want to modify, let's see, the column, I have a list of columns here. I can change the values as I want, but I'm not going to do that now, so close. And I can do the same thing for my slab. Let's take the Members table, slab table, and because I'm currently on the 6th floor, it will preview all the slabs on the 6th floor. But if I want to show other slabs, I'll click all stories. This is the slab type, and this is the thickness of the slab. I can change any value I want. The dead load, life load, I can change the cover for the slabs. When I'm done, I just close. Then we'll run the building check, run building analysis tab, building model check to see if the building is okay, to check all this stats. So no errors were found on our model, so we just close this. Let's go back to pre-analysis to set up the project parameters and the materials for this model. But we've done that already, and if you missed that, you have to go back to my website and apeledesigns.com and download the video on setting up projects. You learn how to set up a project or import from a previous project. I will close this now. And next we come to loading combinations. Loading generator. We insert our wind load. We'll leave other settings for now. I'll click OK. It has included the wind load to the loading combination editor. Move to P data analysis. The P data is a non-linear effect that occurs in every structure where elements are subjected to axial loads. If we check it, and as we see here, approximate slenderness checks using moment magnification method will not be applied when P data analysis is performed, and the analysis calculates the additional force due to P data and then merge it with the design of the members. If you want to apply, you can apply. Then we'll move to see our load cases. We have the wind load in X direction and wind load in Y direction. And we have the notional loads here, and we have the life loads and dead load. And we'll click OK, and we'll click OK. Then we'll move to story loads and parameters. We'll expand all stories to see this clearly. In this section, we are going to be inserting the force of the wind and the direction is acting on the building from the origin. These are the values for notional loads, and they are going to be 0 to run analysis on the structure. Values for the wind load and the point it's acting. You have to understand that Prota structures or Orion does not calculate wind loads automatically. It will involve you doing manual calculations, and you insert these values in these boxes. But I'm going to show you how to do that now. So before we go there, we are going to explain what this means. So I'm going to launch my AutoCAD. phi. I'll make this simple illustration to explain what happens in the story and parameters section of Prota structures. Firstly, we have to consider our model on an infinite graph book with an origin. This is this point. So every point on the software has a reference from the origin. We'll be given the center of gravity from the origin, which is SG on this section, and what we want to find is XC, which is the center of elevation from the origin. We can easily use our measure 2 to find the center of gravity from the very first point and the center of the building from the very first point. If we can determine the difference between the center of building and the center of gravity, which is SD, we can add this value to the center of gravity from origin to get the center of elevation from origin. So this minus this will give us this little, and this little difference will add to the center of gravity to make the center of origin. What I did here was to export each floor of my model to AutoCAD, and we have floor 1 to 4 here, 5, 6 and 7. You have to do that also. And we have the dimension of the x-axis of the building. That's what I took from this very point to this point, and for the y-axis from this point to this very last point. The center of gravity, I try to locate it from this point also, which is the very first point of the building, along the x-axis and the y-axis also, and that's what's denoted by these red dimensions. The center of the building, that's midway the x-axis and the y-axis, and that's where they meet here. So to get this point, all I did was to divide the building into 2. This very point is the point the load in the y direction is acting on the x face, and this point is the where the load in the x direction is acting on the y face. The center of elevation, that's where they meet. The difference between the center of elevation and the center of gravity will be my xd, and this xd is what I will add to the xg to make my xc, which is the component of the wind load. The values you get for xc, we'll fix it in these boxes, and for the wind load, we'll use the wind load formula. So let's begin our calculation. We are going to use Excel program for this calculation, so launch your Excel. And I got this table from Reynolds Reinforced Concrete Designer's Handbook, the 10th edition, and they are on table 13. So to start, we'll start with our story level 1 down to story 7. The story height, and all stories are 3 meters, so we start with 3 meters. And drag it down to story 7. Next will be our basic wind speed, and I'm going to use the basic wind speed of 36, but you use the value in your area. So I use value of 36 for my basic wind speed and take it down to the 7th story. Okay, and the basic wind speed is in meter per second. The next will be to find the design wind speed, which is also in meter per second. So I'll start with getting my value for S1, S2, S3 and multiply it with my basic wind speed. So let's start with S1. The values for S1 is 1, but if the structure is affected by very exposed hill slopes and crests where wind acceleration is known to occur, we are going to use 1.1. and if the site is enclosed by steep sided valleys and completely sheltered from winds, we'll use a value of 0.9, but I'm going to be using a value of 1 to the very top floor. And next will be S2. S2 is the multiplying factor relating to the height above ground and wind breaking. To get the values for x2, I'll use this table. We'll come down to the maximum vertical or maximum horizontal dimension. Let's take it to our drawing. This is 29 meters, 18 meters. So it's less than 50 meters. So we'll be using this part of the table and a topographic factor of 1. So I'm more concerned about this line, and this is the height of the structure. So we'll go back to our table here. We have a height of 3, so I'm going to use this value for 3 meters from ground level, and for 6 meters I'll use the next value, which is within that range. I'll do the same for here, and here too. 15, I'll upgrade it to 0.99, and we have 1.01 here and 1.05 here. Next one will be S3. S3, the value for S3 is 1, and this corresponds to an excessive wind occurring once in every 50 years. So I'm going to use 1 here and take it down to the 7th floor. Now we can calculate our design wind speed, which is in meter per second, by multiplying these values here. Vs is equal to basic wind speed multiplying factor relating to topology multiplying factor relating to height above ground and wind breaking, and multiplying factor related to life of structure, S3, and close this. Okay, you can reduce or increase your decimal places. Reduce, increase. I think I'm good with 2. So you take this down, and next will be to calculate our wind pressure, and this is the formula for wind pressure. It's in Newton per meter square, WK. It's equal to 0.613 Vs square and okay, we take it down to the 7th floor, and we'll convert this to kilonewton per meter square. By dividing by 1000. Take it down. And this is the value for our wind pressure in kilonewton per meter square. Before we go any further, we have to check if our calculation so far is correct. We'll have to go through our values. I think I have an error here. This is supposed to be 0.99. This is okay. Then we'll move to the other part of our calculation, which is finding the center of elevation from the origin. We'll start by inserting the dimensions for the building. Let's start with dimension in direction 1, dimension in direction 2, center of elevation in direction 1, center of elevation in direction 2, and this brings us to our AutoCAD file again. So this is the dimension in direction 1 for 1, 2, 3, 4 floors, 5, 6, and 7, and so their values. So we insert these values in our boxes here. So let's start for direction 1, which is 29.5 down to the 4th floor, 16.7 on the 5th floor, 15.0 on the 6th floor, and 6.9 on the 7th floor. And this will be for direction 2, so we insert these values here. So we start with 18.7 down to the 4th floor, and 18.7 for the 5th floor also, 13.2 for the 6th, and 9.8 for the 7th. To get the center of elevation, we just divide these values by 2. So we start with this, equal to this divided by 2. Take it down for the center of elevation in direction 1, and we'll do the same for direction 2. Value divided by 2, and take it down. The next will be to insert our value for center of gravity in direction 1 and center of gravity in direction 2. Brings us back to our file again. And since I've done this already, I located my center of gravity from this very point. So I'll insert these values in my red dimensions in direction 1. So I think what I have there is 18.4 down to 34. Center of gravity 7.7, 5.9, 3.1, and this is 7.4 to the 4th floor, and 7.7 on the 5th floor, 5.6, and 3.6. Remember our illustration. We want to get the center of elevation from the origin. We get this little difference between the center of the building and the center of gravity. Then we add this little difference to our center of gravity from origin. To get the difference, subtract these values from these values. So we start with the direction 1, which is C minus G1 equal to this minus this, and take it down to the last floor, and do the same for here. This minus this, and we'll take it down. Then we'll go back to our Prota structures to get the value for SG and YG. So this is the value for XG in the first floor, value for YG in the first floor. So we'll be copying these values in the boxes from the first to the 7th floor. This is the value for SG on the 7th floor. So we'll copy these values on our Excel. So let's start 16.4 down to the 4th floor. 18.5, enter. 17.1 and 17.7, and we set the values for YG 13.4 down to the 4th floor. 13.5, 11.7 and 12.9. We add these values to these values to get our distance from origin to the center of elevation of the building, and also these values to these values to get the distance in the direction 2. So let's start with this. Now our XC in direction 1 will be this plus this, and we'll take this is okay. We'll take it down. XC2 equals to this plus this, enter. I'll take it down. So this is the point the wind force is acting on the building. So let's calculate our wind force now. Start with RY, which is the force in the Y direction. And to get this force, we start with this equal to the length of the X face multiplied by the height of the floor multiplied by the wind pressure. We'll take it down. I will do the same for the wind load in the X direction. Acting on the Y face. Height of the floor and wind pressure. Take it down. And this is the value of the wind force acting in the X direction on the Y face, and this is the wind force acting in the Y direction on the X face. What we are going to do now, we're going to copy these values into our Prota structures. So come to Prota structures, story parameters and loads, click OK, and we insert the values here. And the values for the notional loads will not be visible until we run analysis on the structure. But to see our notional loads, we just close this, do a simple analysis, We're not going to tick on any of this, so just start. And when it's done, we'll click OK. We'll take it back to pre-analysis, story loads and parameters. Expand this so we can now see our values for the notional loads. We insert our wind load values. So we'll start with Rx. We'll copy the files from our Excel sheet. I think the first one I have is 30.7. And the component here is 15.35 on story 1. So for the RY, I have 48.44 and 17.71. So I'm going to do this for other floors. Okay, and if you have a 20-story building structure, this is how you're going to manually input all your loads. So when you're done, you click OK. Then we'll come to model options. In the model tab, we can adjust parameters related with the analytical models here. This button is used to change all our settings to default. The story degrees of freedom, we have 4 of them here: X, Y, and torsion permitted. We have the X, Y permitted, and torsion prevented. For the only Y permitted and only X permitted, we use them to define the degrees of freedom of a single frame system, and also for a 2D system defined along the unrestrained direction. The rigid zone. Rigid zones formed at the column beam intersection are important in determining the effective lengths of members. In order to consider the cracks that can be formed in this intersection, we have to reduce these values by a certain amount to calculate more realistic effects. So if I was to set it to maximum, we'll be using the full member section dimension for the rigid zones and calculate the member forces at the member faces. If I reduce it to, let's say, 25%, the member section dimension will be reduced by 25% to form the reduced rigid zones, and hence we will calculate the member forces at a distance 0.25 times the effective depth from the member faces. If we set it to none, we will not take rigid zones into consideration, and we will calculate the member forces at the member axis. But I'm going to select reduce by 25%. The beam section, we'll set it as rectangular, and we'll leave all this like this. Then we'll move to shear wall model. We talked about this earlier. The next thing we'll talk about is the slab model. If we set slabs to define rigid diaphragm, rigid diaphragms will be calculated by examining the continuity and neighborhood of slabs both in horizontal and vertical directions. If we set it to single diaphragm per floor level, this will force the whole story level to behave like a rigid diaphragm, even if there are no slabs defined. And for no rigid diaphragm floor levels, rigid diaphragm action is not utilized in this analysis, but I'll set it to this. We'll talk about this later. Then we'll move to stiffnesses. Modulus of elasticity, moment of inertia, torsional stiffness, and cross-sectional area can be scaled by using these coefficients in this tab. If I give a value then less than 1, we'll be reducing the related parameter. But if I give a value higher than 1, we'll be increasing these values. Take for instance, if you want to minimize the lateral load sharing of columns in a wall frame structure, you can use the coefficient of 5% for column moment of inertia. Hence, we'll insert a value of 0.05, and this will reduce the moment of inertia by 95%. And I think this is what's written here. Then we'll move to settings. We have issue warning for cantilever beams not marked selected. If you want to print wall and beam section properties in pre-analysis report, and you can select this as you want. This takes us to the total horizontal drift limit. This is a ratio of the floor horizontal displacement to the height to the level of the floor. So let's say if the total height to the level of the floor is 13,000 mm, if we multiply it by this value, that will be our maximum total allowable displacement. And for the relative horizontal drift limit, this is a ratio of the relative floor horizontal displacement to the height of that particular story. So if the story is, let's say, 3,500 mm, multiplying by this value will give us the value of the maximum relative horizontal displacement between each floors. The Axial load comparison tolerance. Prota structures or Orion compares vertical loads on the building before it's transferred to the beam and after it's transferred to the beam before analysis is carried out. A third check is performed by summing the column axial loads after the analysis. The three values must be similar. A tolerance value is what we are going to insert here in percentage. We will be issued a warning if it exceeds our tolerance value here. For the story weight and center of gravity calculations, if we use undecomposed slab loads, then there are no beams in the system. It's likely going to be a flat slab, but we're not going to use this. We're going to use the decomposed beam loads. So the masses in the beam joints are used in the center of gravity and weight calculation. Let's go back to our pre-analysis, story loads and parameters. And if you notice, these values here have changed. We click OK. Then we go back to model options, settings. And this is the angle limit for splitting beam axis. You can change this if you want. To take us to the analysis, we'll perform the building check on this structure. If we select building analysis, it's going to perform a linear elastic static analysis for every on-stage load cases that has been defined, and a stage construction analysis is performed for every stage construction load case. We have the date of our last analysis here. Eigenvalue analysis, we'll just need this for seismic design purposes and also when wind tunnel test is required. So I'm going to leave this for now. If you check on these boxes, the software will do a batch design of the column and beam reinforcements, but we don't want to do that now. If you want to select a new bar type that you just added, you can check on these boxes. And I'll run my analysis by clicking start and you wait for it. And when it's done, we just click OK. The next will be to view our Axial load comparison report. We'll launch it. The Axial load comparison report helps us to verify the total dead load and life load applied to the building. It's used to check if the slab loads are correctly decomposed to the supporting member and if the gravity load applied matches the building analysis total vertical reaction. The first check will be to see if the sum of undecomposed slab loads is approximately equal to the sum of decomposed slab loads. With this, I think the difference is a little. And we'll check if the total decomposed applied dead load is similar to that of the total delta G. So this is this value here, and this is delta G. So it's similar. It's okay. The difference is not much. The next will be to check if the total decomposed applied life load, this value, is similar to that of the delta Q. The difference is not much. Now that our check has passed, it means our analysis is okay. But if it doesn't pass, you have to go back to your model, check for the warnings, and you check if the discontinuous columns are properly supported. We'll close this. We'll move to post analysis. The model analysis results display helps us to view our results graphically. So I'm going to click this. This is our model. To zoom in, we'll move the wheel of our mouse forward and move it outwards to zoom out. You can orbit. We hold right click on the mouse and move. You can pan by holding the center wheel and moving. Okay. This is the general tab. You can display it in plan bring it back to perspective view. You can zoom in here or zoom out. You can view from an angle. You can switch between orthogonal view and perspective view. You can print, save this preview as an image or copy the image. Let's go to elements. These are the nodes, support nodes, and we also have load nodes. To display the label of the nodes, we just activate this, but we don't need this now. For springs and for diaphragms, to activate diaphragms, we'll click here, and these are the diaphragms. Can hide this. To hide our frame elements, we'll click here, preview. To view the labels, we'll click this. To view our frame number, we'll click this. Local axis, direction, rigid members, and loads. If you want to find a frame element or node, you come to General tab, find. If you know the node number, you just type it here and to point at it. If we click find, when we're done, we clear or close. If you know the frame element number, let's say 200, you can find and it will show us the frame elements. Same thing for share elements. So let's clear this and close. Then we'll move to results. Let's get a better view for this structure. I think this is okay. Zoom out a bit. No. Okay, this is fair. To view our displacements or deactivate displacements, we can click here. So no displacements will be shown. We'll bring them back. We'll move to the right hand side. If we click on our dead loads, we can see the effect of the dead load on this building if we animate. And this is the effect of the dead load on the building. You can switch to another load case to see the effect on the building. You can switch to this, and you can switch to wind load to see the effects on the building. And these are load combinations. On the left hand side, we have our view settings. Let's deactivate this. You can change the color and text of your labels. Let's go to filter. You can filter to preview just a story or multiple stories. You can filter to view just an axis. Let's view axis 7. Let me pan this a bit so I can see it clearly. We can view our shear force diagram and bending moment diagram for this frame in different load cases. So I'll pick on the first load case, zoom in more, review my diagram. Let's start from here. Shear force diagram. If it's too small, you can increase the scale by clicking here. To view the labels, we'll click here. Let me zoom in more. Okay, this is good. Can switch to view more diagrams. The scale is too small, we can increase it. Let's deactivate this. We can come to elements to view our loads. You know, these values will change in different load combinations. If I switch to the next one, the value changes for this load combination. Load values will change for this other combination. Okay, let's deactivate this. So basically this helps us to view our analysis results graphically and print them if we want. Let's close this. Now we've completed the analysis on this structure, but still it's not valid because the structure contains point load, the area load and the line load, and has a waffle slab and a roof slab. If it was a simple structure, we can stop here at this point, but because of these other features which require finite element analysis, we have to do a finite element analysis on the structure. I'll discuss this in the next video.